So good afternoon, everyone. I'm Yimo, and I'm a postdoc researcher at the University of Hong Kong. Actually, delighted to be here to have the opportunity to give a presentation of my research at the Icio 2026. Today, I will be sharing the topic of our work on a reliability central framework for structural failure prediction in high-rise modular buildings. So first of all, let's introduce some background. Modular building is an industrialized construction approach. In this mode, a building is divided into three-dimensional modules or volumetric units that are fully prefabricated in a controlled factory setting. These modules come complete with structural elements, including mechanical, electrical, and plumbing service, all before they are transported to the site and rapid assembly. This technology already gained significant traction in many countries like UK, Singapore, China, and Australia. By leveraging highly standardized designs and factory-based production, modular construction not only supports the
updates of the panels, dynamic scheduling, project completion, dates forecasting, as well as collaborative decision making. To develop the DT mode system, we use the DSR, or the design science research method, where we first started by the research input, which are the challenges in the current research on the progress monitoring of modular construction, and as well as the research motivation. The second stage of the DSR method was to develop the DT mode system, and this includes a variety of tools, including the discrete event simulation, computer vision, building information modeling, the game engines, and real-time data input. In the third stage of the DSR method, we illustrated the system using a case study, and in the last stage of the DSR method, we used scenarios to illustrate the features of the DT mode system. The development of the DT mode system included 6 main components. The first component was the virtual environment, and this is based on the type of the environment. If it's existing environment like a facility, we use the laser scanning. If it's an environment that will exist in the future, we use a 3ds Max tool or the Autodesk Revit. The second component of the DT mode system was the real-time data input, where we collect the data from the physical environment using different sensors, such as computer vision, RFID, QR code scanning. And then once these data are collected, we pass it to the dynamic or the cloud simulation model, where we update the parameters of the simulation model based on the collected real-time data. The fourth component is the parameters of the DT mode system, where these parameters are being updated based on the sensor data to update the status of the panels in the implementation stage of modular construction. Then all of these components together are integrated within the game engine environment. In this case, we use the Unity 3D, and then we can export our end user application for the DT mode system for the users to interact with. The data transfer in the DT mode system follow 2 different methods. From the physical to the digital model, we collect the data using laser scanning, RFID, computer vision, and other sensors. And once the data is in the digital model, we do our calculations, and then we send the data back to the physical model in source of alerts and schedule updates. To develop the virtual environment, we first look at the type of the virtual environment. So if it's an existing facility, we use the laser scanning method. So we scan the environment, and then we have our points cloud. We import it into 3ds Max tool, and then we build our 3D model, and then we pass the model back to the DT mode system. On the left-hand side here, we can see an application on the virtual environment method. So this is the existing facility or the existing manufacturing station for the floors in the factory, and this is the reflection of this facility in the DT mode system. Other virtual environments that are related to the project. So we have the BIM model in one of the Autodesk tools, and then we import the model into the DT mode method, as well as the transportation roads. We build them directly into our Unity 3D editor. To illustrate the DT mode system, we worked on a case study of wall and floor wooden panels, a production line that are sending these panels to 10 different projects. Each of these projects, they have their own demand of walls and floor. So on the left-hand side here, we see the physical environment, and on the right-hand side, we see the DT mode system. So once the panels enter the site, there are some codes that are installed on each of these panels. Each panel has a unique ID, and once this code is scanned, it sends a signal to the virtual model, and we can see the updates of the panels in the virtual model that can be arrived, stored, or installed. Similar, when we install a panel, the codes are scanned, and then it sends a signal to the DT mode system, so the DT mode user can see this update in real time. In the factory, the computer vision system collects the information about the production, and once it captures certain behavior in the factory, it sends the signals to the DT mode system, and then the DT mode user can get updated about number of floors being manufactured, the duration of the activities, how many workers are engaged in particular activity, and so on. As I mentioned before, the duration of each of these activities, they are not fixed. They are, as we can see, there's a fluctuation in the duration of each activity. So the computer vision system capture the activity and capture the duration of each activity, and then it sends this duration for the DT mode system. Why is this important? Because when we simulate the project completion dates, at first we have this blue solid line for the baseline schedule, but when we move through with the project and we simulate again for this update 1, now we use the most recent duration data for the activities, and then we simulate again. And then, as you can see, we have an updated schedule with this orange dotted line that is finishing in a later date than the scheduled date. And then we move again with the project, and then once we simulate again, we use the most recent information, and this will give us a better or a more accurate completion date for each of the projects. If we take project C as an example, the initial completion date was around April 10th, but once certain data are collected from the physical environment, this completion date was finishing around April 20th, and then like more information came, and then we simulate again, and then this project will finish around May 1st. The DT mode user can access the features of the DT mode system using an end user application, where one or more of the DT mode user can be integrated within the same decision-making environment. Also, the system features other KPIs, including wall inventory and floor inventory in the factory, as well as the carbon emissions that are being emitted through the life cycle of the project. To this end, this paper presented the DT mode system that targets the real-time collaborative decision-making to enhance the monitoring of modular construction project using a combination of virtual reality and sensing technologies. We use the DSR method to develop the DT mode system, including the research input, the development of the system, the illustration of the system, and the proof of concept. We also used in the development of the DT mode system, we had 6 main components. We presented a case study to illustrate the features of the DTMOS system, as well as a proof of concept method with different scenarios to show the features of the DTMOS system. And that's it, and thank you so much.
Thank you. Okay, let's have one or two questions. Quite interesting presentation.
Reliability. So the next step is such as the left figure. So the subsystem interaction importance to the system failure. And the IMC to MSC dependency has a strongest effect around like 0.08. So connection maintenance should be the top priority. And the right figure shows the reliability lifetime distribution. The mean time is like about 51.6 years, and the model failure time around 53 years. This probability estimates both uncertainty-informed maintenance and the renewal planning. And here comes the study results. First, the subsystem dependency, especially from MSC to IMC, drives a sharp rise in the system failure risk after 25 to 30 years. Ignoring this dependency gives an over-optimistic prediction. Second, IMC is the dominant contributor to system failure with the effect size around 0.08. So maintenance should prioritize the connection over each other subsystems. Third, the estimated system lifetime centers around 50 years, and importantly, our framework can integrate the field data and adopted life cycle management. Thank you, that's all. Thank you for your listening, and open the floor for question and discussion.